So today's topic is what I introduced towards the end of the last lecture. The consequence relation. I said this is the hero of the course, so we should all be respectful. And this is the notion. So let's remind ourselves a little of how we got to this. So in general, a first order logical language L, as usual, is given by some parameters, and then we have the notion of an L structure, where D is the domain and this is the interpretation map. You have interpretations for the constant symbols, function symbols, and predicate symbols in the language. And then you have a bunch of variables, countable set of variables. And then we have the notion of an L model with an assignment pi, which maps variables to domain elements. And then we define this notion of alpha being true in model M. Then we said if alpha is a sentence, which means free variables of, okay, I usually write phi. Phi is a sentence, just to remind yourself. It has no free variables. In that case, we actually write phi is true in structure S. This is important to keep this distinction in mind. Basically, when you have fully quantified statements where there are no free variables, in that case, we just need to look at structures and say that in this structure, this sentence is true or this sentence is false. And where you have free variables, we need some assignment of values to free variables, which is what is done by models. This is the principal difference, and it's good to keep that in mind. Okay. So then we said we can talk about models of phi or models of alpha for a formula in general to be class of L structures S such that, so this is the class of L structures on which phi is true, right. So in particular in the language of groups, if you write down the group axioms, right, how many of them are there? Whatever number, finitely many take their conjunction, that is a sentence. Remember, there are no free variables and that's a class of groups. This is exactly how we do our business, right. And in the language of order, remember we can write sentences for saying that the relation is irreflexive, the relation is transitive, the relation is total. Take the conjunction and that gives you the class of linear orders. That's the class of L structures, the class of orders that satisfy this, and there's the class of linear orders, etc., etc. And this is how, and this is the basic building block like of our whole enterprise, which we started by saying that we provide languages for describing mathematical structures, and those structures are given by this. Now, sometimes we are not lucky where we just write a few statements. Maybe we might write infinitely many statements. Typically, for instance, when you have some parameter, some number, for instance, and for each number you have an instance of an axiom, right? Do you know of any such thing? Do you know of any situation where you write, like in the case of group axioms, there are so many of them. Okay, that's easy. Linear orders, I said. Okay, maybe you can come up with. Let's see. So in general, and then we started looking at this question. Given a model M, So given a finite model M, so the next thing that we started looking at was is alpha true in the model? Is this sentence true in the given structure? You are given a finite structure and you want to know whether sentence is true, and we talked about how you would go about it algorithmically. I hope you thought about it. Any questions related to that? Last time I said I gave a very hand waving style of outline of how you might go about solving the problem, and I said you think about it. Did anyone think about it? Any questions?
If the formula is for all for all x alpha,
Yeah.
then
So let's say there is an x inside. So let me write this, use this notation. Yeah.
and I mean, how do we go about checking if this formula holds in the model? Do we do this for all the elements in the domain?
Absolutely. You have to look, you have to do it for all the elements in the domain. So for instance, let's say, I mean that formula is nothing much, right? Let's say it's something like this. Yeah. Now you have the interpretation for P. You have the interpretation for Q. What will they be? What will be the interpretation for P? Your structure, what in this little language will be a structure for you now? A domain with an interpretation for the predicate symbol and for the, and these are unary, right? So you'll have, let me call this xp and xq, both are subsets of D, right? That's what it means. Yeah, is it clear? Both are subsets of P, and now what should you do? You have to look at every element D, right? Take x assigned to D, so now you take this and x assigned to D1, you want to check whether Px implies Qx. X assigned D2, check, and so on. There are k elements. Well, once you have assigned D1, what do you have to check here? Well, you want to check if D1 is in the set XP, then D1 is in XQ as well. If you find that, put a tick, keep going. If you put a tick for all of them, answer yes. Otherwise, say at some point, if you find that some DI belongs to XP, but DI does not belong to XQ, say no, right? This is, but you want a uniform algorithm that works for whatever structure that's given, right? So you have to do a little bit of work, yeah. But yeah.
So when the input is so when the algorithm is given the input, that is the model and the formula.
Yeah.
So the model also contains the all the domain elements.
You're given the finite model, so you're given the finite set and an interpretation for all the, yeah. Somebody else, there was something. Okay, so what I'm going to do, I was planning to do it during the weekend. I'm sorry, I forgot about it actually. So I'll send you a set of problems that actually walk you through the steps for the algorithm, right? Basically, the way to go about it is develop something where there are no variables at all, right? Do this whole business for an, you develop the whole algorithm for formulas where you are guaranteed that the formula has no variables whatsoever. What's the joy of that? Well, what kind of formulas are these? Oh, let's think about them, right? What kind of formulas will you have? There are no variables in the formulas. That means your terms are made up of only constant symbols and function symbols. And when you have equality, again, no variables, right? So you can have, you just have arithmetical expression perhaps, it depends on the language, right? So you've got some equalities to check, and then you have Well, you may have relation symbols, k-ray relation symbols, whatever, but you just have to do a table lookup, right, in the atomic case. And then when you go further, there are no quantifiers. Think about how you'll manage all the bureaucracy for this. Once you do that, you are in business, okay? And then consider all formulas which also now have variables, but no quantifiers. Think of how your algorithm will go. Modify your algorithm for, I'll send you this, as a bunch of questions for you to solve, and then you will see that there is a systematic way to go about it. And once you have done that also, then to do with quantifiers is fairly straightforward because you just have some extra work to cycle through all these. Yeah. Okay. So then we'll take it up after if you have any questions. So coming back to this, actually, yeah, okay. Sorry, I'll put this back. So there are some, we saw several kinds of examples that day of different kinds of formulas, right? I mean, for instance, suppose you have got your language is yeah, there is a binary relation in the language and nothing else, right? Some binary relation. Now, what are the kind of examples we were talking about? For all x, for all y. What does this say? What does it say about the relation R?
Hello?
Yes.
So if the domain set is D,
Yeah.
then the relation R is D cross
D cross D, right? So try to write various formulas like this, right? I mean, then it will also give you some idea of what formula says, right? I mean, without that, really cannot proceed. What about what about this? Yeah. What does this say?
is D set.
Yeah. What does it say about the set? Somebody.
It is the empty set.
No, it doesn't say that. It says it's the empty relation. The set can be whatever it can be, right? There is a difference. Last time I was writing formulas, it said it's the empty set in that language, but this is one where it's saying that the relation is empty, right? It's not saying anything about the domain itself, but the relation doesn't have any tuples in it. Okay, so my suggestion is that you try to cook up some things, right? I mean, cook up some things and write. It's all that it takes, right? And what about, yeah, for all x there exists y 6. These are the most fundamental things to remember. What does this say? For every element of the, we write it right, for every element of the domain there is an element in the range and so on, right? That is the sort of, whereas this one is something else, right? Everybody has a mother, right? That's, if R xy stands for, mother of x is y, yeah, everyone has a mother is what it says. The other one says there is one person who is the mother of everyone, yeah. And well, you can write such funny stuff and look at it also. What about Rxy implies Ryx? What does this say? It says nothing, huh? It's not, I didn't write for all x, if I write, of course, for all x, for all y, right? I mean that it's a symmetric relation. But if I don't put any quantifier and if I just write this, well, it depends on what your x and y are. It depends on the particular relation that you have got in mind and the particular elements, then it either true or false. So it depends on all that, right? So it takes a bit of living with all this stuff. What about this? Does it depend on x, y? There is no assignment. It should be clear that this is a contradiction and this has got no models at all, right? It doesn't matter what assignment you give to x and y, it's false, right? So here is a sentence that has no models at all. I mean, there is a, well, I can make it a sentence if you want. Has no models, right? And even if I have it without variables, it has no models. So in general, one is to say that in this particular structure or in this particular model, my formula is true. Another is to say, does my formula have a model at all, right? What about something like this, the most trivial thing again that we can think of? It should be clear that this is going to evaluate to true in any model whatsoever, independent of what assignments you give to x and y. So, true in every model. And same thing for all x, for all y. So, you given a formula, it may have no models at all, it may be true in every model, or it may be true in some models, not in others. As a sentence, it may be true in some structures and not true in some other structures, or it may be a formula with free variables, and it may be true over some structure with some particular assignment, but with a different assignment, it may be false over the same structure. All these possibilities are there, and they are all interesting, right? I mean, I'm not saying anything deep. It's fairly obvious, I guess, in what I'm saying. So, and these kind of, yes?
Sir, I have a doubt.
Yeah.
The contradiction statement for all x for all y are of x, y and not of r x, y.
Yeah.
Couldn't it be true in the empty set?
No. That's the point, right? Well, what about, let's look at this, right? This one, this is true over the empty relation. Right? Where the domain is arbitrary, but the empty relation. When I consider the empty language, right? When I write for all x, x not equal to x, look at this statement. For all x, x is not equal to x. Yeah? What are the models for this? This is true over the empty set. Because it says if I take any element of the domain D, when I consider the model variant, I want to check if it, but there is no element at all in the domain. Therefore, in fact, if I write any formula, no, I don't want to write, yeah. Yeah. So this formula is true over the empty set, right? If I write this, has no models. When you assert there exists an x such that x is not equal to x, there is no hope of finding a model for it. You see the difference between the two, Siddharth? Yeah?
Yes, sir.
So this has a model. This has a model which happens to have the empty set as the domain, right? And this has no models at all. Yeah?
Yes, sir. So here we are taking for all x and for all y.
Yeah. Where? Here. Yeah.
Yes, sir.
So this is the point, right? It does. No. Ah, yeah, that's true. You are absolutely right. If I have, that's true. This is true. This is true over the empty set exactly for the same reason. You are right. So this has, yeah, this has empty set, has no models. Thank you. You are right. This is one reason why you will find, if you look at Anderton's book, or if you look at certainly Anderton, Mendelssohn's book, several logicians, if you look at mathematical logic texts, they will define a model, a domain, I mean a structure to be a domain that's non-empty, and so the whole thing is defined with, so that they don't want to admit such cases, this kind of absurdities where you can make mistakes. Yeah. So, but we didn't do that. We said, so we live with the problem and we have to be careful, right? Like you're just pointing out. Thanks. Okay, so as I said, now there are various categories of sentences, so that's also worthwhile. Yeah. Sentences that are sentences true, I'm saying trivial L structure. Given any L, the trivial L structure is the empty set, right? Interpretation is vacuous because there is nothing to, nothing to assign anything. So that is the trivial structure. Sentences true only over this trivial structure, and then sentences not true in any structure. And similarly now, and of course sentence is true in some structures and false in some structure. Of course, I am saying this for sentences. Similarly, we can talk about models, right? Formulas that are true in all models, formulas that are true only over, well, yeah, think about that. What will you do with formulas? Can you write formulas true only over the trivial models? Okay, something to think about. What about formulas that are not true in any models? Formulas true in some models, and so on. Yeah. So, and these are sufficiently important to give some names. I am not going to worry about the trivial models, the trivial structures for now. Let's only consider these. We say that, I think it's gone. Alpha is valid that is for every m, for every L model m, m makes alpha true. This is the notion of validity, and we say that alpha is satisfiable if for some L model m, m satisfies alpha. And it's a nice proposition to observe that alpha is valid if and only if negation alpha is not satisfiable. This should be clear, right? Suppose alpha is valid. That means what? Alpha is true in every model. Now consider negation alpha. Well, can it have a model? Consider that model M. Well, since alpha was valid, M must make alpha true, but we have just picked up a model for negation alpha, so that model must satisfy both alpha as well as negation alpha, which is not possible against the semantics of negation. So if alpha is valid, you cannot, not alpha does not have a model, that means it's not satisfiable. Conversely, right, suppose not alpha is not satisfiable. We want to show that alpha is valid. Suppose not. That means there is some model in which it is not true. But in that model, negation alpha is true. But we assumed it was not satisfiable. Okay. Make sure that you understand this. This is the, so these are dual notions, and this is what we usually. Yeah?
When we talk about valid and satisfiable, are we given a like structure?
No, we are just given a language. Given alpha, which is an L formula, you say it's valid if it is true in all L models. It is satisfiable if there is some L model, right? We fixed a language L, right? So we are considering the class of all L structures and L models, and over which we are talking about. Yeah? So you are fixing the vocabulary, and therefore, and you have a formula in that vocabulary. So, and what is clear then is that we can extend this notion, right? Instead of talking about a single formula being variable, satisfiable, let gamma be a set of formulas. We say that gamma is satisfiable if for some L model M, what do we want? It makes all the formulas in gamma true. For some model M, for all gamma, maybe I shouldn't use this, for all gamma belonging to gamma, yeah, right. There is a model that makes all of them true. This is also a very interesting notion, right? It's interesting because you gamma may be a finite set, maybe an infinite set, right? And what we are saying is that this model makes all those formulas true, right? Notice that this notion is interesting only when gamma is infinite. Suppose gamma is finite, what happens? Suppose gamma is finite. What does it mean to say that gamma is satisfiable? Is the same as saying there is some model M such that M satisfies alpha 1 through M satisfies alpha M. From this, what do we know? We know that it satisfies the conjunction of all these, right? Then M satisfies. By the way, of course we write such things even though it's not there in the language, right? In the language you have only a binary connective alpha and beta. So when we write alpha and beta and gamma, we mean this and so on, right? Yeah. So if it's a finite set of formulas, satisfiability of a finite set of formulas comes down to the conjunction of all the formulas in that set, which is the same as what we had for a single formula, right? So the notion is not particularly interesting if gamma is finite set, right? So we have the notion of a formula being satisfiable if there is a model for it, and that's good enough to work with finite conjunctions of formulas as well. What is very interesting is when gamma is an infinite set. When, because we cannot write this. Remember, I can't write alpha 1 and alpha 2 because there is no infinite conjunction in the language. If it's a finite conjunction, bracketing is okay, right? I can bracket as I like. And the semantics of and if you go over, it makes sure that you can bracket as you like and you won't go wrong, right? But this is not there in the language, so therefore this is actually a very interesting notion. So, given a set of formulas, you would like to know whether it is satisfiable. Given a single formula, you would like to know if it is satisfiable. So, clearly that's another very interesting algorithmic question there. The next algorithmic question to think about, but we are not going to take it up now. I just wanted to mention it. And we know that this is the same as, I'll go to prime, given alpha, right? Algorithm for one is the same as an algorithm for the other, as this is, right? If you have an algorithm for checking validity, you can use it to check for satisfiability. If you have an algorithm to check for satisfiability, you can check for validity. And how do you go about this? This, in some sense, this is much easier to think about than all that nonsense that I was doing last time, right? Last time we had given a finite model M and a formula alpha, I wanted to check that alpha is true in the model. But for that, I have to first define what is a finite domain. And then I said, finite structure, finite model. Okay, finite model when the underlying structure is finite. Structure is finite if the underlying domain is finite. But then came the question of how do I interpret all the constant symbols and all. I said, anyway, we have to look at the formula. Formula mentions only, some 3.5 constant symbols, 4 functions. It's a finite vocabulary that alpha will fix for you. In terms of variables, just look at the free variables in alpha. We do all this, right? That's because the particular model that's given may be a cruel model in which you have to sit and check all sorts of nonsense, right? But this seems like a much simpler problem, right? You're just given a formula alpha. You construct any model what you like, right? This is about the free, tremendous freedom, right? You are given a formula and somebody gives a formula like there exists X, there exists Y. What was that? Px implies Qy. Or right? I mean, what's the problem, right? You have to come up with a set and you have to come up with an interpretation for P, Q and R that makes it true. Very easy thing to do, right? And maybe somebody will write something like this: for all x there exists y, x less than y, right? Okay, you start with some x and then you have to produce something x greater. Yeah, you have to produce something greater. Maybe you have to keep doing something. I mean, what's the problem, right? Why should I worry about it? I mean, who says that this has to be interpreted as an order relation of any kind, right? This is just a binary relation, give it whatever interpretation you like, right? So, it seems a much simpler problem to think about because all you are given is a formula and that formula is, remember, it's presented as a tree, right, for you, right? And what's the problem, right? If it's a conjunction, just make sure that both sides you build a model and put it together somehow. If it's a disjunction, any one of them will do, right? Keep going. It all seems like, and if it's there exists, guess something, guess an element, put it in, right? So there is a way of thinking about it and I hope you will try, right? Because it is worth thinking about. And can I build a model? Can I build a finite model? Maybe you might have to, maybe the formula doesn't, have finite models. It has model, but every model for it is infinite. When does that happen? Can I write a formula at all for which if it has a model, that model has to be infinite? Well, consider the language of order since I have used this here. In the language of order, I write for all x not x less than x, for all x, for all y, for all z, x less than y and y less than z implies x less than z. If you want, let me just remove these, yeah. For all x there exists y, x less than y. Now, and I take the conjunction of these, right? So what kind of an order that I want? Well, I want some elements, right? So let me write. This is very important, right? If I didn't have it, from these I can only force something to happen if you have some elements. Maybe there are no elements at all, right? Consider any model for this. What can we say? Suppose there is, let M be a model, right? S be some structure. What kind of structure it will be? It will be a set with some interpretation for this. We know nothing about that interpretation, right? Some binary relation. But now what can we say? Well, we are told that there are two elements, right? There is at least one pair in that, right? Call it AB. Well, and then, well, for A we have an element. So, in the domain there must be at least two elements A and B, right? Okay. Can they be the same element? Can it be a single element? It's not possible because that the pair AA cannot belong, the pair BB cannot belong. So AB are two distinct elements and the pair is in the tuple. But now B is an element in the domain, so you need to have something here. What about, so maybe I can have BA. That's not a problem. But then this one says if A is less than B and B is less than A must belong, which is not possible. So I cannot throw in BA. So indeed I must have some BC. I might as well call this A0, A1, A1, A2, and then you will have A2, A3 and so on. You should be able to set up an induction and show that, you know, any model that satisfies this formula should have, you know, D must be infinite, right? It must have a countable subset in it, right? So this is a formula that forces infinite models. So when I start with a formula, I have no idea how the formula is going to be. Maybe this is a formula that I have been given. So if I am looking for a model, I may have to construct an infinite model. So my algorithm may have to check whether this formula has a model by doing something clever, right? It doesn't mean that it has to construct something infinite. Here, for instance, we can see that it will become infinite. Now we can see, maybe you can build it into an algorithm, right? So, so there is a lot of freedom in this, but those who are trained in algorithms will also know that, you know, freedom is a terrible, you know, comes with a terrible price to pay. I mean, right? Too much freedom is very bad, right? So that's what is bad about this also, but it's something that you should think about. And exactly like I said about thinking about the algorithm for checking whether alpha is true in a given model, where I said the first step is to think about looking at a formula which has no variables at all, right? And then look at formulas with variables but no quantifiers. And then we'll get to formulas with maybe with variables, no quantifiers, with function symbols, without function symbols, then get to things with quantifiers. We can do it in steps. Same thing one can do here also. And I assure you that it's very instructive to think like that, and you might find some interesting insights. I'm not going to go down this. This is a topic that we'll come back to later on. As I said, I want to look at something which I introduced here. So for instance, what have we got here? right? We have got something which says I have got a linear order, right? And then I want to say something like this, right? Take this formula, this sentence phi, and I want to say from phi, what is it that I can conclude? And this is really what, take any model of phi, take any linear order, I want to know whether this particular sentence C is true over linear orders, right? And this is really the game that we are really interested in mathematics, right? That, so this defines linear orders. We want to ask, is the sentence C true over linear orders? In the language, in the language of order, you consider sentences true over arbitrary orders. Now I am coming down to those that are true only over linear orders, right? That's exactly like I said in the language of groups. You write the group axioms and you want to know, is this true in some particular group? Is it true in all groups, right? And then supposing I put the abelian axiom, I want to know what is true over all abelian groups, right? And you can go on putting structure by adding formulas and keep asking more interesting questions. In fact, in the language of order, I already said many things that they talk about dense. We can talk about dense linear order, etc., and then you can ask questions over them. Now, this is precisely the same question as what I'm talking about here, except that I don't want to think about only some finite conjunction of formulas, but look at infinite set of assumptions as well, where my axioms, yeah.
Can I just interrupt? This is Purandar.
Yeah.
Is it really a linear order because you didn't add the axiom that every two elements are comparable?
Oh yeah, that's true. I should. For linear orders, I must add that for all x, for all y, x equals y, or x less than y, or y less than x. Absolutely. If I want linear orders, I do have to add that. At that earlier moment, I was only talking about that being infinite, but this is what is needed for saying it's a linear order. Thank you. Yeah. So, notice that that's really what this is about. So, what is the definition of the consequence relation? This is defined by, for every model M, L model M, this is assumed, if for all gamma, in gamma, M satisfies gamma, that's exactly what we are saying. Consider any model that satisfies all the assumptions in gamma, then it better make alpha true. So, this is how I have described a class of L models, right? In particular, consider the case where it's a set of sentences and you want to know whether a particular sentence follows as a logical consequence. This is really how what we call alpha is a logical consequence of gamma or semantic consequence of gamma. This is semantics because that is a symbol we use for defining the semantics. Yeah. So this says that consider the class of structures that I have defined using gamma. I want to know whether alpha is true over this class of structures. In the special case of sentences, in the class of models in general. And at once we see from what we had been talking about is that if gamma was finite, so if gamma is finite, let me write beta 1 through beta n. What does this mean? I'll write if and only if this should be easy to see. Suppose alpha is a consequence of this set of formulas. That means what? Take any model M. If it satisfies all of them, then it must satisfy alpha. If it satisfies all of them, it satisfies the conjunction, right? So then this is valid as well. I mean, the way to do it, assume this, suppose this is not valid. Then if it is not valid, what does it mean? Valid means it's true in every model. Not valid means there is some model that makes this false. How can a model make an implication false? It should make all this true and then this false. Well, if it makes all this true, that model satisfies each of these. So it satisfies all the thing. By assumption, then M satisfies alpha, and that is a contradiction. Conversely, assume this is valid. Let's show that alpha is a logical consequence of this. How do you show that? Well, you must consider some model M that makes all of this true. Then it satisfies the conjunction. Therefore, that model must satisfy alpha, which is what we want. So it's clear that this is not an interesting notion if gamma is finite. Well, we already have the notion of validity. It's not a new notion. Well, it's an interesting notion, but it's not a new notion, right? So, and to reflect, by the way, we'll also, maybe I'll leave it at that. So, this is an interesting notion when gamma is infinite. That's what I wanted to say. And there are other cases that we considered last time. So, let me remind you, if gamma is empty, what does it mean to say alpha is a consequence of the empty set of assumptions? Well, what does the definition say? It says take any L model M if it satisfies everything on the left hand side. Well, then that applies vacuously, therefore we must check this, that M satisfies alpha, right? So therefore that is the same as saying sorry, alpha is true in every model M. So to reflect this is a notation that we use. We write notation alpha is valid. Nothing on the left hand side. So to write alpha is valid, typically you write the turnstile alpha with nothing on the left hand side to remind yourself of this. Well, another thing that I talked about was what if gamma is a contradiction? I don't need to have equality. Let's say gamma contains a contradiction. In which case we can see that for every model M, for every formula alpha, because again apply the definition. To show this, what should you do? Consider any model M if it satisfies, well, there are no such models, right? So the left hand side is something, so the implication is vacuously true. Sorry? So the implication is vacuously true. That's what it, because the assumption is false. Take any model M that this cannot happen, and therefore, so this is the property of this consequence relation, that a formula is a consequence of, any formula is a consequence of a contradiction. That's why you say a contradiction is absurd, because from that follows any formula whatsoever. And some people call this explosion. Very dramatic, right? Once you have a contradiction, the whole thing explodes, right? The consequence relation explodes, as they call it. So you can choose whatever terminology you like. So you can see that this relation is very interesting. It's got already many properties that we had talked about. One is in the case when it's empty, when it's contradiction, when it's finite, and more to go. Another property that is of interest, and this is monotonicity. Suppose gamma is contained in gamma prime, right? Now what can we say? And alpha is a consequence of gamma prime. Yeah, no, sorry. Alpha is a consequence of gamma. Then alpha is a consequence of gamma prime as well. Let's see why, right? We are already given that alpha is a consequence of gamma, right? I want to show that by increasing the assumptions, whatever I had earlier shown to be a consequence do not become false. That's why we call it monotonicity. By enlarging the set of assumptions, by weakening the set of assumptions, whatever I have established continues to be true. And this is very important in mathematical reasoning. Right? In mathematical reasoning, we want to say we build up some knowledge and we say that over this class of structures, something is true. Now I go over to, I'm adding more assumptions, right? I'm making it, that means what? Somehow I have to, anyway, let's look at the formal details, right? This is what we want to show. To prove this, what should I do? Take any model M. Suppose it makes all of gamma prime true, right? Well, then gamma is contained in it, therefore it must make all of gamma true as well. Therefore, by assumption, that model satisfies alpha, and we are done. So, and this is a very important assumption, property of this consequence relation. There are, I think these are probably the most two important assumptions that you should keep in mind. There is another way of thinking about this monotonicity, and this is as follows. Let me maybe write here. I said mod alpha to be the class of models M such that, yeah. Now I can generalize this to mod gamma. It's the class of all models M such that it makes all the assumptions in this set true. Consider all the model, I mean a model for gamma means what? It makes all the formulas in gamma true. Now I can talk about models of this set of gamma, formulas to be this set here. There is a dual notion that is already interesting that you can see. Let kappa be a class of models. I am saying these things for models, but as I said, it suffices to only consider structures and sentences in these things, because that's really how we apply these things. Free variables create a lot of complications, just carrying it along because that's how we have the definitions, but this is enough for, structures are enough for many other things. So let me call it th of kappa to be the set of all alpha such that for every m in this class, m satisfies alpha. Exactly the dual notion here. What does this say? This says collect all those formulas which are true over all the models here, right? If you have a class of structures, right? Class of, for instance, in the language of graphs, right? With the binary relation, I am interested in the class of connected graphs, right? So I am saying consider statements that are true over all connected graphs. All graphs are bounded tree width. It doesn't matter. Whatever your quantification is over, right? So this is of course models. This is, and you read this as theories. Theory. The theory of the structure is, of this class of structures, is all those formulas or all those sentences that are true over all the structures in this class, right? And this is precisely why we call it, when we say graph theory, right? We mean, right, we fix a particular language, over that language, all those statements that are true over that class, the class of finite graphs typically, right? Though graph theory is not only about finite graphs, but typically that's what you will read. And then you say, okay, the class of all graphs, right? Category theory, right? It doesn't matter. Group theory, ring theory, This is exactly the formal meaning of these in the language of mathematics that you build. Now, monotonicity is saying something very interesting here. It should be easy to see that if gamma 1 is contained in gamma 2, then mod gamma 2 is contained in mod gamma 1. The mod map is anti-monotone. Why? Well, let's see. Suppose gamma 1 is contained in gamma 2, right? Now, consider any model that makes all of gamma 2 true. That's what this means, right? Since it makes all of gamma 2 true, it makes all of gamma 1 true, therefore, it's in mod gamma 1. So, this makes sense, right? If I increase the set of assumptions, the class of structures that satisfy it reduce, contract. So, this is how logicians say, as theories expand, models contract. As models expand, theories contract. This is exactly how we understand it. Like I said, you talk about the class of groups, and then you talk about the class of abelian groups because you have added extra assumption of abelianness, right? So this is there is a very nice correspondence here. Similarly, if kappa 1 is contained in kappa 2, then theory of kappa 2 is contained in the theory map is again anti-monotone, and again it should be easy to see. This is precisely what we have in mind, that the class of structures, right? Yeah, that's right. As the class of structures expand, you are diluting, right? That's what it really means, right? Once you have added, then you are actually diluting. Okay. So now, of course, so this is so now we can talk about given gamma, right? Given a set of formulas gamma, I'll call this con gamma. The composition of the two. You take gamma, look at all models that make all of these true, and look at all sentences that are true in over all these models. That's what the composition will be. And it's a very easy observation to see. Alpha belongs to con gamma if and only if gamma turnstile alpha. That's why this is called the logical consequence relation. Alpha is the consequence of gamma according to this, if and only if alpha belongs to theories of models of gamma. That's exactly the definition. Parse through the definition and make sure that you understand, right? And as I said, that's why this is the thing of interest. And notice that this composition relation is very nice. Okay, so what I have written here, the mod map is anti-monotone with respect to inclusion. So also the TH map. The composition is monotone, which is what we were talking about earlier. That means if gamma 1 is contained in gamma 2, then TH, that is con gamma 1, the logical consequences grow monotonically. And as I said, this is a very important characteristics of classical mathematical reasoning that we do, and typically this is what is called classical logic, right? And with these kind of properties. So this is in fact, and then there are more interesting things. Gamma is always contained in con gamma. It should be easy to see that gamma is always contained in con gamma. Why? Well, if alpha belongs to gamma, surely why is this true? Check the definition, right? Suppose alpha belongs to gamma. Take any model M. If it makes all of gamma true, well, alpha is in particular sitting there, therefore alpha model M makes alpha true as well. That's all that you are using, and this says that gamma is contained in con gamma, and then it should be easy to see. Well, from monotonicity I already have this, right? Therefore, I have con gamma is actually contained in con of gamma, right? Because by monotonicity we know this is true. As it happens, the other direction is also true. So con of gamma. So this is an exercise. Apply the definitions and show that this is true. An operator with these properties is generally called a closure operator. Okay, so this is a closure. And why do I, this is all terminology, right? Why do I say operator and closure and all? Don't worry about it. This is good enough as a definition for us, right? Basically, the moment you apply it twice, it saturates and it's monotone. Gamma is contained in this, that's a good enough definition, right? So it's got some nice properties. So this thing is called a Galois closure, and these Galois pair theories and models. So it's got many more interesting things to say about it. I'm just mentioning it to say that it's sufficiently interesting for you to take a look at, and if you are interested, I can tell you a lot more about these things later on, right? But this is an interesting notion that we want to study. Now, as I said, whenever there is a definition, one should also have an algorithmic question in mind, right? Like for instance, the next question will be algo 3. Problem is, what is given gamma? When gamma is finite, this is the same as algo 2 prime, as I called it. Algo 2 was given alpha, is it satisfiable? Algo 2 prime was given alpha, is it valid? Well, because if it is finite, we have already seen that you are only checking for validity of a particular formula. Take the conjunction of the left hand side, ask if that implies the right hand side, right? So not very, this is the same as this. So the question is, when gamma is infinite, well gamma is infinite but presented in some finite fashion, okay? We don't know what that means, how do you finitely present an infinite set of formulas? But if you could find some way of doing that, this would be a very interesting question to ask, okay? Now, let's get back to the earlier question, which is of satisfiability, right? Now, can you think of, I want to move from a formula being satisfiable to a set of formulas being satisfiable, right? That's what we were talking about. Let me ask this question. Give me a set of formulas gamma such that every formula in gamma is satisfiable, but gamma is not. Yeah. In fact, you can give me a finite set of formulas gamma such that every formula individually, if I take, every formula is satisfiable, but the whole set is not satisfiable together. So that we understand this notion of what is a set of formulas being satisfiable, right? That means simultaneously you should give a model that makes all of these true. Yes?
So we can,
Yeah.
hello?
Yeah.
So we can take, like, can gamma be finite?
Yeah, I'm asking for a finite gamma.
Okay. Then for example, in theory of group, we
Yeah.
can take one formula
Yeah.
be for all x for all y, for all x for all y, x dot y is equal to y dot x,
Okay.
and the next formula will be for all x for all y. It is not true that for all x for all y, x dot y is equal to y dot x.
Right. So obviously two formulas will do, no? I mean,
Yeah.
what groups and things, right? I just have to say Px, not Px. Yeah? How about this? I mean, each formula is satisfiable, but the whole set is not satisfiable. Okay, so give me a set of, okay, so this is trivial, right? How about gamma having three elements where every alpha belonging to gamma is satisfiable, every pair is satisfiable, but the set is not. So I can't, every pair is satisfiable. That means if I take any pair together, that should be satisfiable as well. I said size 3, but make it larger if it makes you happier. Yes? I want three formulas, each of which are individually satisfiable. But if I take any pairwise conjunction that is satisfiable, that's what it says, right? Pairwise conjunction are satisfiable, but the whole conjunction is not. Anyone? Use the recipe that I was using, no? That I gave you for 2. How would you generalize that for 3? What is it that you're looking for? Together, two of them should collaborate to make the third guy false, right? That's the sort of thing we are looking at. Except that not particular 2, but any 2. Okay? If you're finding it hard to think about, here is one candidate. A failure of transitivity, so to speak. Px implies Qx, of course it's satisfiable, you can always build a model for it. Qx implies Rx, of course is. And then I've written Px and not Rx, right? You can't have all the three of them together satisfiable, because Px implies Qx and Qx implies Rx will actually give you an implied implication Px implies Rx, and this is Px and negation Rx. So together they are not satisfiable. Now check that. Yeah, any pair is satisfiable. If I take any pair, it doesn't matter, because Px implies Qx. Supposing I want to make this true and I want to make Px and not Rx true, well, what should I do? Make P true for a particular element, right? P true, Q true, but not R. That will take care of it, and so on. Yeah.
Yeah. Sir.
Yeah.
Hello.
Yeah.
So one more example will it be P Q and not of P and Q.
No, not of, the moment you put not of P, you are dead. You said P as well as negation P, right?
Not of P and Q.
Okay, that's not P or not R. Yeah, sure. I mean, after all, I can do it using OR, right? This is the same as not P or Q, not Q or R, and P and not R. So, yeah, sure. I mean, this is only a recipe. You can write whatever you want. There are many ways of coming up with the answer. So, clearly, and here is an exercise for you to take up and do. Given any k, construct a set gamma of k formulas such that every proper subset of gamma is satisfiable, but gamma is not. Yeah? Given any k, come up with a set gamma k such that every proper subset, like I said for pairs and so on, right? It doesn't matter. Even if, so every proper subset means what? You are allowed to omit at most one formula, right? If I look at, yeah, every proper subset is satisfiable, but the whole set is not. It's a nice exercise to take up. So what is all this telling you? This is telling me that with finite set of formulas, okay, the set, the entire set has to be taken seriously. That is why we talk about this notion being so important, making all the assumptions true, right? So making proper subsets true is not going to help because maybe one of them will create trouble in building models, right? When you build a model, you have to build a model simultaneously for all of them together, right? That's what this says. What about an infinite set? We are doing all this with finite sets. Maybe what about infinite sets? Exercise, construct an infinite set gamma such that, well, every proper subset, well, that's too much, right? Simpler thing is to consider every finite subset. But gamma is not. I mean, it seems reasonable to proceed along these lines and say that if every finite subset means what, right? Because I can pick larger and larger formulas, right? It doesn't matter how large that is, right? If I pick every finite subset, I find it to be satisfiable, but the whole set is not. How do you go about doing that? You understand the question, right? Here we have seen that as far as finite sets are concerned, because look at this k, that k is not playing any role, right? I'm just saying that it's possible to build, when it comes to finite sets, it's possible to build finite set of formulas such that every proper subset is satisfiable, but the set is not, right? That's all we are saying, right? Because it's a finite set, it has got some cardinality, so I'm saying with k, right? That's only to help you solve the problem in a particular way. How do you do that for infinite sets? It makes sense, right, that it should be possible to take this recipe and extend it further so that for infinite sets as well, yeah, I mean, this should be possible, right? Proceeding along the same lines, we should be able to say that, okay, take any finite subset, I can write a formula for that, and take anything larger, well, we can keep going, but there must be something larger that is not satisfiable, so the whole set is not satisfiable, right? Now, if I were a nasty guy, I would just leave you with this exercise and make you, you know, break your head over it, but I'm not a nasty person, I'm a nice person. So let me tell you that this is not possible. And that's a very non-trivial statement, that somehow when you go to infinite sets, this kind of constructions actually break down, right? What are we saying? Not possible is the same as saying if every finite subset of gamma is satisfiable, then so is gamma. Note that the statement makes sense only for infinite sets. If gamma is finite, it's trivial. Every finite subset includes itself, so it's completely trivial, right? So it's non-trivial only for infinite sets. So what are we saying? That now this is not obvious at all, and it's not only not obvious, it's sufficiently important, and this is the first theorem of the course. So this is the theorem, and this is called the compactness theorem, probably one of the most celebrated theorems of the subject. Gamma is satisfiable if and only if this direction is trivial. And this direction is quite non-trivial. Nice to write, proofs like this, right? Okay. This direction, what does it say? If gamma is satisfiable, right, there is a model that makes all of gamma true. So of course it satisfies, that makes every finite subset true as well, so you are done. What about this one? This says I give you gamma and I am told that every finite subset is satisfiable, right? That means you pick finite subsets, you keep going, and for each of them there is a model. Somehow from all these models, it asserts that you can put together and build a single model, right? You can stitch together all these models to one model. And I use the word stitch together because there is actually a construction which tries to stitch these things together. It's a very nice algebraic proof, but we won't go through that. So we are going to spend some time doing this proof. Okay, this is as I said, the first theorem of the course. It's a non-trivial statement, and the building blocks are very interesting because we learn a lot in the process, and will be of something paisa vasool later on. But what is amazing is that this definition here and this statement here have a very nice connection. So let me just mention that in the time that we have today. So this is a very nice little observation. I said, given gamma and alpha, I want to check whether alpha is a consequence of gamma, right? Now, if gamma was finite, right, of course I can bring it down to validity. So it makes sense to ask, given gamma and alpha, is there a finite subset of gamma 0 of gamma, such that right? And this is a very reasonable question to ask, right? Gamma is, let's say, an infinite set. Gamma is some infinite collection of formulas. Alpha is one single formula. I should be able to look at alpha. After all, remember, alpha has mentions only some finitely many, its vocabulary is finite, right? It's got finitely many free variables. Let's make it a sentence so that they're not even free variables, right? Everything is quantified. You should be able to look at alpha, go back to gamma and ask, which are the particular ones that affect alpha. The truth of alpha out there like alpha is a consequence of gamma, I want to check, but I mean, it seems reasonable to expect that there is actually a finite subset from which alpha is a consequence, right? Out of all those assumptions, I can track down to finitely many assumptions that actually give alpha as a consequence, right? Now, if this were true,
Sir,
yeah, sorry, yeah,
sir, is alpha a consequence of gamma?
yeah.
What is it?
Oh, sorry. Given such that, sorry, of course, yeah, yeah. So I'm saying to check whether alpha is a consequence of gamma, I would like to check some finite subset. Of course, how to find that finite subset is another question. But if there exists one, then of course I find that finite subset and I can check for validity. This is a reasonable program to carry. So I would say this is a wish, if only it were true, right? Yeah. And what is very interesting is that this wish is actually granted. And what is granting it is the compactness theorem. Okay. So, and this is a worthwhile statement. So, let me write it as a lemma. So, here is a lemma. Let gamma be a set of formulas and alpha a formula. The following are equivalent. And what are they? What are the equivalent statements? One, gamma what we as a wish. If alpha is a consequence of gamma, then there is a finite subset of gamma such that alpha is a consequence of that finite subset. This statement is actually equivalent to if every finite subset of gamma is satisfiable, then so is gamma. This is the non-trivial part of the compactness theorem. In fact, if you want, you make this an equivalence. Again, this direction is trivial. Why? Suppose there is a finite subset of gamma which is called gamma 0 such that alpha is a consequence of gamma 0. By monotonicity, anything larger also alpha is a consequence. So this is in fact an if and only if, and well, and conversely, let me write, even though it basically the statement of the compactness theorem. So these two are in fact equivalent, but the interesting direction is only this way, so let me just leave it at that, right? So this is what is interesting. So these two statements are equivalent, and why? I mean, it's not even clear why they should be equivalent, right? A priori, what is this? But that's precisely the content of the compactness theorem. For that, to understand this, let's look at what this definition.
Here, one question.
Yes.
So here you have, are you assuming gamma is some countably infinite set?
Gamma is infinite is what I'm assuming, because if gamma is a finite, this whole, of course, it's all true. Huh? If gamma is finite, everything is true.
It's true, but I mean, given the nature of infinity is
No. The language is countable. Remember, okay, when I say infinite, it means countably infinite set of formulas. Why? Because the language itself is a countable, right? So we can have only countable. So we can look at languages of arbitrary cardinality, compactness theorem also over arbitrary cardinality, and so on. But I'm not going to worry about that now. And because there are generalized notions of compactness also, right? Because then you take some cardinality that is gamma of some cardinality lambda, and you want to prove that if every subset of lesser cardinality is satisfiable, then the whole. So you can do all that, but that's a terrible game to take up initially, and
Right.
So other question is this quantifiable, the first thing?
Yeah.
I mean, can we quantify the size of gamma?
Well, you would be rich and famous if you could, but yeah. Yeah, you cannot. Okay. So, thereby hangs a tail, as they say. We'll take it up later, right? Yeah. Okay. So, yeah, to think about this, as I said, we'll take it up. I mean, we'll take up the lemma, and also, as I said, the compactness theorem, by the way, will take at least a couple of sessions. So, make sure that you follow, right? It's a fairly non-trivial statement, and it will take some time to work through the various building blocks. And we are not even going to prove it fully for whatever we start with. So, I warn you. What does this mean? Alpha is not a consequence of gamma. What does this say? Apply the definition and tell me what that is. There is a model M that makes all of gamma true but falsifies alpha, right? Another way of saying, it makes all of gamma true and also negation alpha, right? It makes alpha false is the same as. This is another way of saying gamma union negation alpha is satisfiable. So these two statements are the same. Alpha is not a consequence of gamma is the same as saying gamma union negation alpha is satisfiable. That's really the connection between those two. The statements 1 and 2, the connection between the two you get by looking at what, not what consequence means, but what negation of the consequence relation means. Okay, that's the clue. Formally, assume this is true, right? But this is false. That means if it is false means what? Every finite subset is satisfiable, but the whole set is not satisfiable, right? From that whole set, you have to pick some element. This is an infinite set, right? So I can always write it as some gamma prime union alpha, right? It doesn't matter. I put negation alpha, you put alpha here, and you will get negation alpha that side. It doesn't matter, right? And well, from that you will say, that thing is not satisfiable. Therefore, gamma prime does not give negation alpha as a consequence. From that, you have to go to this finite subset. From that finite subset, you have to argue that that finite subset is unsatisfiable. Here we were told that every finite subset is satisfiable. It's the kind of jugglery we have to do. We'll take it up next time, right? And go over the proof. Yeah.
I'm confused a bit. Sir, like is 1 or 2 like not true by itself? That if
That we have to prove, right? I mean,
like what I'm asking is
this
like,
one,
like
no.
one true by itself.
That is Oracle telling you it's true, right? I called it compactness theorem doesn't make it true. I mean, that writing it a theorem means we hope it's true when we manage to do the proof, right? Right now I'm saying these two statements are equivalent. Both are true or both are false. As it happens, both are true, right? So your wish is granted. That's why I said the wish is granted. This is what we wanted as a wish. In fact, Vikram has a stronger wish. He doesn't want just some arbitrary subset, but some bound, right? Okay. But that wish, I don't know whether it's granted or not. But at least existence of a finite set, a subset can be granted, right? But we'll prove that. But when we prove that, then we know both of these are true, right? This will come out as a corollary. But right now, I'm just saying that even to understand the statement a little carefully, it's good to see that the content of the statement is the same as the content of the statement, right? So proving this helps us think about these kind of relationships between formulas and sets of formulas, right? After all, as I said, that is the whole point of the whole course, right? understand relations of this kind. Any other question? Okay, so we'll start with that lemma and go over to the proof of the compactness theorem next time. Okay, thank you.